three major steps in the production of aluminum. The first step is the mining and processing of the ore, bauxite. Next is the refining operation, in which the aluminum oxide, or alumina, is extracted from the ore. The third step is the smelting process, where the alumina is reduced to aluminum. Now, this film is concerned with the refining process, in which the alumina is extracted from the ore. Alcoa has three such refining plants in East St. Louis, Illinois, Bauxite, Arkansas, Mobile, Alabama, and in 1956, construction was begun on a new plant at Point Comfort. Well, now, let's see how we extract the alumina from the bauxite. Bauxite is made up of aluminum oxide, silica, iron oxide, titanium oxide, and water in both the free and chemically combined state. Well, now let's look at another chart to see how we get rid of these impurities. Now, these impurities, silicon, iron, titanium, and water, are represented by these symbols on the chart. And almost all of them must be removed from the alumina. Normally, the alumina can contain not more than 1/10 of 1% impurities to be considered suitable for the production of aluminum. Now, we use what's known as the Bayer method, which is a chemical process containing several steps. After the bauxite has been ground to a fine powder, it's fed into a mixer with a solution of hot caustic soda, which we get by adding crushed lime, soda ash, and hot water. And then after this mixture has been thoroughly mixed, it goes into a digester. Here the alumina goes into solution as sodium aluminate, a liquid. The oxides of iron and titanium are insoluble and easily separated, but the silica reacts with both soda and alumina to form an insoluble compound. Now, higher temperatures increase the amount of alumina that will dissolve, so these steel digestion tanks are heated by steam under pressure. The mixture goes to a tank where the pressure is reduced, and then to a filter press, where it's filtered through heavy cotton cloth. Now, the sodium aluminate solution, being a liquid, passes through the cloth, but the solid impurities remain on the surface. And these are washed with jets of water, forming a red mud, which is pumped off as waste. The silica, however, has combined with some of the soda and alumina, which means a loss of some of the alumina. We now have a clean solution of sodium aluminate. This is made up of caustic soda and alumina and combined water. Our next step is to get rid of the soda. The solution then goes to a cooling tank and then into a large precipitator tank. Here it's cooled and agitated, and a seed of aluminum hydrate is used to stimulate the precipitation. The aluminum hydrate is essentially alumina and combined water. Now, when it's been separated, the caustic soda goes back into the system to be used again. Some dissolved alumina remains with the soda. The aluminum hydrate then goes into a thickener to free it from any remaining soda. And the final step is to drive off the combined water, and this operation is called calcining. The solution is passed through a drying kiln, which is similar to the kiln used to dry bauxite, except that a much higher temperature is required, about 1,000 degrees Fahrenheit. The solution goes into one end of the slowly revolving kiln and emerges at the other as alumina, which is a compound of aluminum and oxygen. After it's been cooled, it's loaded into covered hopper cars and shipped to our smelting works, where the alumina is reduced to aluminum. In this film, we're going to describe briefly the smelting process, the third and final step in the production of aluminum. Now, the first operation is that of mining and processing the ore bauxite. Then, at a refining plant, the aluminum oxide, or alumina, is extracted from the bauxite and shipped to the smelting works. Our smelting works are located at Alcoa, Tennessee, Baden, North Carolina, Messina, New York, Point Comfort and Rockdale, Texas, and at Vancouver and Wenatchee, Washington. The smelting process involves separating or reducing the aluminum from the aluminum oxide. This is done in steel cells lined with carbon. And these are called smelting pots. Rows of these pots are connected electrically, and normally 2 rows of cells are called a pot line. Now, the separation of the aluminum from the oxygen takes place in the pot by an electrolytic process. Now, so that you can more easily understand this operation, let's take a look at a cutaway diagram of a smelting pot. The alumina is carried in by conveyors and loaded by crane into storage hoppers above the pots. It's released from the overhead hopper periodically and fed into the pot, which contains a bath of molten cryolite. This cryolite acts as a solvent and dissolves the alumina. You'll notice that the pot also contains rows of carbons submerged in the bath. The electric current comes in on this bus bar, comes down through the carbons and through the bath. The electricity separates the aluminum from the oxygen, and then the aluminum, being heavier than the cryolite bath, settles on the bottom of the pot. The oxygen unites with carbon, forming carbon dioxide, which escapes as a gas. Now, the bath is kept in a molten state at a temperature of above 1700 degrees Fahrenheit with the heat generated by the electricity. And the smelting pots require constant attention to keep the operation going without interruption. Alumina must be added to the bath at specified intervals. The crust that forms on the top of the bath must be broken in periodically. And carbons must be kept lined up correctly so that they'll not take more than their share of the current. And the smelting operation is a continuous one. From time to time, the aluminum at the bottom of the pot is siphoned off or tapped into large crucibles. From here, the molten aluminum is either transported to a holding hearth for further processing, or it's poured into molds to form pigs. Now, another type of smelting pot, known as the Soderberg, is in use at our Point Comfort, Texas, and Alcoa, Tennessee works. The same electrolytic principle is used in the Soderberg method, but instead of several carbons or anodes, a single large carbon is used in each pot. It's enclosed in a casing, and a carbon paste is put in from the top. Paste is baked by the heat of the bath, and as it's used up, more paste is again added from the top. Now, whether we use the Soderberg or the pre-bake method described earlier, we get pigs of commercially pure aluminum, which are usually remelted and alloyed with other metals and poured into ingots, which are fabricated into thousands of aluminum products. The purpose of this film is to describe briefly our major aluminum fabricating processes. First, though, let's review the steps that are necessary to produce primary aluminum. We begin with the mining of the ore bauxite, which contains aluminum oxide. Next is the refining operation in which the aluminum oxide, or alumina, is extracted from the ore. The alumina is then reduced to commercially pure aluminum at our smelting plants. The metal may then be poured into what we call pigs, such as this, or it may be transported to a holding hearth in a molten state. This is known as hot metal transfer. At our Messina, New York, Alcoa, Tennessee, and Vancouver, Washington works, where we have both smelting and fabricating operations, the molten metal is transported directly to the remelt department. If pig is used, it must of course be remelted. The aluminum is then alloyed with other metals to obtain the desired properties of hardness, strength, and durability. Some of the most common alloying elements are copper, manganese, magnesium, silicon, and zinc. After alloying, the metal is poured into shapes suitable for fabricating. These shapes are called ingots, and their size and form will vary depending on the fabricating process to be used. The two most common types of ingots are produced by the tilt mold method and the DC or direct chill method. One type of tilt mold ingot is produced in a rotary casting unit at our Cressona, Pennsylvania works. The molds are tilted so that the metal will pour smoothly, eliminating turbulence which causes air pockets. As the unit revolves, the metal cools and hardens, and finished ingots are automatically ejected from the molds. Now, to produce DC ingots, the metal is poured into a trough, and from here it is fed into individual metal molds, which extend into underground pits. Water-cooled jackets around these molds cause the metal to solidify into ingots. As they emerge through the bottom of the molds, the ingots are further cooled with a spray of water. At Messina, a somewhat similar method known as the liquid top process is used. In this liquid top process, the molds are made of graphite, and the tops of the molds are submerged in a pool of molten metal, kept at a constant temperature by heating units. For this method, it's not necessary to control the flow of metal into each individual mold, since they're all supplied from the pool or liquid top. The long ingots are later sawed into sizes suitable for fabrication. Another less common type are these granulated ingots used in the production of steel. These are produced at our Wenatchee, Washington works. Most of our fabricated products are made from the tilt mold and DC ingots. Our major fabricated products include plate, sheet, foil, extruded shapes such as these, tubing, and rolled structural shapes, and bar, collapsible tubes, and other impact extrusions, wire, rod, cable, screws, nails, bolts, and other fasteners, and pigments for paint. To make aluminum plate, the ingot is heated to the proper working temperature and passed repeatedly between the rolls of a rolling mill to break down its cast structure and to reduce it to its proper thickness. The plate may be cold rolled by other mills to produce sheet. Cold rolling hardens the metal, and often it becomes necessary to anneal or soften it at intervals by a heat treating process. Now, in this manner, the aluminum may be rolled into flat or coiled sheet of any desired thickness. At our Davenport, Iowa works, we produce tapered sheet for aircraft wing sections on a large rolling mill which we operate for the Air Force. By rolling the sheet thick at one end and thin at the other, much expensive machining is eliminated. Sheet may be converted into foil by further rolling through a series of mills until it's thin enough for its intended use. The rolls of foil are sliced into lengths suitable for commercial use at the time of shearing. Aluminum sheet, plate, and foil are produced at the Alcoa, Tennessee, Davenport, Iowa, Edgewater, New Jersey, and New Kensington, Pennsylvania works. At our Messina works, aluminum rod, bar, and other structural shapes are rolled in much the same manner as sheet. The main difference being that the rolls, instead of being smooth-faced, have grooves designed to produce the shape desired. Several different rolls are usually required to bring the shape down to its proper dimensions. Now, another method of making aluminum rod is by a continuous casting process. Rod is produced by this method at Vancouver, Washington, using equipment known as a Properzi unit. Structural shapes are also made by the extrusion process. Now, to produce extrusions, the ingot is heated to the required temperature and placed in the cylinder of the press. An hydraulically operated ram forces the metal through an opening in a die at the other end of the cylinder, and the extrusion takes the shape of the opening in the die. Alcoa's extrusion plants are located at Lafayette, Indiana, Cressona, Pennsylvania, New Kensington, Vernon, California, and Vancouver, Washington. At Lafayette, giant extrusions for the Air Force are produced on a press with a force of 14,000 tons. The extrusion process is also used in the production of seamless tubing. Hollow ingots are placed on a bar or mandrel in the press cylinder. The mandrel controls the inside diameter, and the resulting extrusion is known as tube bloom. Now, this tube bloom is then placed over another mandrel on a drawbench and pulled or drawn through a die. The die determines the outside diameter of the tubing. The inside diameter is controlled by the mandrel. Several draws may be necessary to bring the tubing down to the desired dimensions. Now, in the smaller sizes, tubing can be drawn in much longer lengths and much faster on a unit known as a draw block. This operates on the same principle as the draw bench. The tubing is pulled through a die, and a small floating mandrel is used inside the tubing to control the inside diameter. On this draw block at Lafayette, smaller sizes of tubing can be drawn and coiled at the rate of about 1,000 feet a minute. Our tube drawing operations are located at our New Kensington and Lafayette works. At Alcoa, Tennessee, an entirely different method of making tubing is used. Flat strips of aluminum sheet are fed into a series of rolls which form the tubing. The edges are joined by a continuous welding process. Aluminum wire is made by drawing rod through dies in much the same manner that the tubing is drawn. Generally, it's drawn through a series of dies to obtain the desired diameter. Smaller sizes of wire may be drawn at a rate of about a mile a minute. To produce electrical transmission cable, aluminum wire is stranded around a reinforcing core of steel. This is known as ACSR. A different type, called expanded cable, is produced by stranding the aluminum wire around a larger core of paper twine covering the steel center. Aluminum wire, rod, and cable are produced at the Messina and Vancouver works. Collapsible tubes and many other types of open-end containers are produced at our Edgewater works by a process known as impact extrusion. Circular slugs are cut or blanked from aluminum sheet or plate. The slug's then placed in a cup-shaped die of a power press. Mechanically operated punch strikes the slug a single downward blow with tremendous pressure, forcing the metal upward in the clearance between the punch and the die. Other fabricated products produced by our company are aluminum fasteners. At our Lancaster, Pennsylvania works, aluminum wire, rod, or bar is fed into automatic machines which are designed to cut threads on screws or to fashion rivets, nails, and other similar items. Another product produced at Alcoa, Tennessee and Logan's Ferry, Pennsylvania is Albron, which is the name given to the pigments used in the manufacture of paint. To make Albron, aluminum pig is melted and blown through special spray guns to form an atomized aluminum powder. The powder is processed in ball mills to form fine aluminum flakes in a kind of sludge. After filtering, it can be made into powder or paste, both of which are used for pigments for paint. Well, that's a brief description of our major fabricating processes. The production of cooking utensils and aluminum closures will be covered in separate films. Of course, many aluminum products are made by various casting and forging processes. Now, most of the items that we've discussed in this film, such as sheet, plate, extrusions, and tubing, can be further fabricated into the many different kinds of aluminum products, including household items, aircraft and automobile parts, building materials, bridge railings, highway signs, and thousands of other products.